In our next section, we're going to look at the routing protocol support on the ASA, and then take a look at a couple examples of doing both static routing and dynamic routing, and then talk about some of the route tracking features that the ASA supports, which adds reliability and essentially upper layer information to static routing. Now, the scope of this for the security exam is not very large. You don't really need to be an expert in the routing protocols. You just need to understand just the basics of how do you enable them, and then how do you secure the control plane. So assume that for all of the different routing protocols, you need to understand how to do any type of filtering and also any type of authentication. So this would be true of RIP version 2, OSPF, EHRP, and BGP. Now, specifically with the ASA, we support, of course, static routing. RIP version 1 and RIP version 2, we can run one process total. OSPF, you can run two processes. EHRP, one process. Now, when we look at the functionality of these individual protocols, it is not nearly as advanced as the functionality that is inside of iOS. So a lot of the basic features that you might take for granted in iOS are not necessarily going to be there under the ASA OS for routing. Now, specifically, some of the features that it does support would be that we could run multiple routing processes at the same time. So we could have an OSPF process on the inside while we have a RIP process on the DMZ. For all the protocols, we of course support authentication, because in main functionality it is a security box. We also support route filtering, but of course that's going to be subject to the normal routing rules. Like in OSPF, you cannot filter routes out of the database. This would be for RIP or EHRP routing. We could do redistribution. If we have different protocols running on different interfaces, we could exchange the information between them. And then when we do redistribution, we can do filtering to specify what particular prefixes we do or do not want to allow. We also support ECMP, equal cost multipathing, for doing load distribution. But there's kind of a strange caveat in this with ASA, is that it's only supported over the same interface. So there is a very limited application to this feature in ASA, and it would look something like this, where if we had ASA 1 in the middle, and then we had an inside interface, and we had an outside segment that is going to two different routers on the same LAN, and then they are advertising equal routes to us. So if we say that all the way on the right we have some prefix X that is being advertised through either OSPF or EHRP or RIP, and the ASA has two equal routes, one of them to the router .1 and one of them to the router .2, this would be a supported design for doing ECMP. So based on the individual flows, the ASA would then distribute the load between the two next hops on the LAN. What would not be a supported design, though, is that if we took the same type of situation, so we have the ASA, we have the inside, but now we have two different outside segments. We have outside 1 and we have outside 2, where this is router 1, this is router 2, and then again they're advertising the same prefix X through dynamic routing. In this particular case, the ASA would not be able to do ECMP. So it's mainly for when you have active routing on the segment, like if you're doing maybe GLBP and the routers are both forwarders at the same time, the ASA would support routing to both of them through flow distribution, but again, only if it's on the same interface. So two outside interfaces you cannot load balance between. One outside interface that you have multiple equal cost routes, then yes, you can do the load distribution. Okay, it also supports route tracking, which we're going to look at with the IP SLA feature. And then it also supports multicast routing. Okay, multicast support is very limited on the ASA. We're going to come back and talk about this later after we've gone through both the routed firewall and the transparent firewall. And then we're going to take a look at the differences between dealing with multicast in routed mode versus in transparent mode. So next I'm going to take a look at the documentation so we can get just a basic idea of what would be the scope of the routing protocols for ASA. So again, let's start back at the main documentation page. And from here we would go to Products, Security, Firewalls, ASA, ASA 5500, Configuration Guides, and then we'll say 8486. Okay, under here this is going to be configuring IP routing. Okay, also if we go back to the ASA documentation, let's go to reference guides and the command reference. Let's say command reference for 8.3 and later. You can see here these are all listed alphabetically. It's not per topic. So there's not something that simply says, you know, this is the OSPF command reference, this is the EHRP command reference, etc. But if we look at, let's say back at the configuration guide, let's say under configuring OSPF, and let's look at an example of this. The syntax is very similar to iOS, so as long as you understand just basic routing logic and how to enable the protocols, that's going to be the vast majority of the things that you would need to do on ASA. So here in this case, they're saying we will first enable the OSPF process, so we're saying this is the process identifier. The interfaces that have anything that starts with the 10 network are going to be in area 0. We have a route map that says if the metric is 1, change it to 5 and set the metric type to 1 as we're redistributing into OSPF. So that is under OSPF 2. It's saying redistribute OSPF process 1 into process 2. And then based on the metric value, we're going to do an encoding of E1 versus E2. So I wouldn't say that you even need to go into this level of detail, but when you look at, like, let's say under OSPF, that's where most of these commands are going to be. So from the command reference, if you go to O, then OSPF, you can see that there's not really that much functionality as compared to regular iOS. So some of this would be related to filtering, like you could say this is a passive interface to say the database filter. If you wanted to do some sort of path selection modification, you could change the cost. Dead interval, hello interval, that would be for convergence. So how long does it take to figure out that the remote neighbor is no longer there? OSPF network point-to-point non-broadcast. We'll talk about this when we get to VPN. This is going to be if you have a LAN-to-LAN IPsec tunnel and you want to run multi-hop OSPF between two ASAs. So this is kind of the one exception where ASA does support dynamic routing over an IPsec tunnel. Normally you just do static routing to say this is the endpoint and then they're reachable out this particular tunnel group. But there is kind of a weird design exception here where you can run OSPF over the IPsec tunnel. And the way you do that is by specifying the network type as point-to-point non-broadcast, and you specify who is the neighbor on the other side. So who's the other ASA that you're trying to route with. Okay, otherwise the big thing is going to be the authentication. So make sure you do spend some time to go through the different control plane authentications. I'm not going to go through all of these examples here because hopefully they're pretty self-explanatory. So let's say in this case we want to run OSPF between router 1 and the ASA, and we also want to do authentication. Now in the case of the router, let's go to the link and say IP OSPF 1 area 0, and on the ASA we will say router OSPF 1, network 136.1.115, and let me turn off logging here. Okay, let's say no logging console. So under OSPF1, network 136.1.115.15, so this particular interface is going to be in area 0. Okay, if we look at router 1, we should see that it generates a log message once they form the adjacency. If we show IP-OSPF neighbors, okay, we see that we learned about the remote neighbor, so this means that the multicasts are getting exchanged between router 1 and the ASA. And we've gone past the two-way state in the OSPF state machine, which means that there's bidirectional communication. So basically they're in exchange start, which is they're starting to synchronize the database. This means that bidirectional communication is fine. And this is going to take a little bit of time based on the default timers for the interface. Okay, so we see that the neighbor is full. Also on router 1, if we look at, let's say, show IP route connected, it has two interfaces. It has the LAN interface, which goes over to the ASA, and then it also has a loopback. So let's say on the loopback, we're also running OSPF. The ASA should then be learning this on the DMZ interface. So if we show route, we see we learned the OSPF route. It's the loopback to router 1, and it's reachable via this next hop on the DMZ. Okay, if we wanted to do authentication, we would go to that link level, which if we show nameif, tells us which particular interface is actually DMZ, because in the routing table, it does not do that correlation between the name and the physical link. So in this case, DMZ is E0/1.115. Here we would say, what's the OSPF authentication? Okay, let's do MD5. What's the OSPF message digest key? So what's the password? Okay, the password is CCIE. On router 1, if we look at the debug IP-OSPF adjacency and debug IP-OSPF hello, we should see now that the packets coming in from the ASA, they're mismatching authentication because the ASA is configured type 2, which is MD5 authentication. Router 1 doesn't have anything configured. Okay, so eventually the neighbor is going to time out. You could see the neighbor relationship went down. In iOS, we would basically do the same thing, just the syntax is a little bit different. We would say IP-OSPF authentication is message digest, and the IP-OSPF message digest key is key number 1, and the password is CCIE. Okay, now the neighbor is up. So hopefully, if you just spend some time in the documentation to look at what are the routing features, most of these are very self-explanatory, and it's very minimum functionality in the ASA versus the iOS implementation, because of course iOS is for routing primarily, where ASA is mainly for security. Now we also saw that on the ASA we did not need to do an exception in order for the routing updates to be received on the local interface. So also let's go beyond this one step, and let's say that we're also going to enable OSPF on the outside and on the inside. So there's three different interfaces here. I have the DMZ, which is security 50. I have the outside, which is security 0, and then inside, which is security 100. So on the ASA, let's say in OSPF1, we're simply running OSPF everywhere. So network 0000 with a mask of all 255s. Okay, this simply says turn OSPF on all interfaces. Now, if we look at the result of this, let's say show run router OSPF. Actually, this is one thing that I forgot about ASA. The syntax is backwards for this. If we go, let's go back under the OSPF process, and let's remove these two statements. And let's say network, question mark. Okay, it says, what's the address of the link? Let's say 136.1.115.15. And what is the mask for the network address? Okay, in iOS, this syntax is a wildcard. In ASA, this is a subnet mask. Okay, we'll also see that this is true for the ACLs in ASA. So iOS uses the inverse mask, which is the wildcard. ASA uses the regular mask, which is like a subnet mask. So if I wanted to match one exact address, I should have said all 255s, not all zeros. Let's say area 0. Area 0. Then show run router OSPF. Okay, we can see it's that exact match. If we show OSPF interface brief, most of the commands, well, it doesn't support all the exact commands. Most of the commands are going to be similar to iOS, with the exception that they don't say show IP. So it's show EHRP, show OSPF, show RIP. But this would tell us what interfaces are running the protocol. And then these are all the individual protocol options. So very similar to what you would see in regular iOS. But previously what I had said in the syntax, if I can scroll back up to it, I had said this here. In iOS syntax, this means enable OSPF specifically on the interface that has the address 136.1.115.15, which is just the DMZ link here. But in ASA, if we look at now the show run router OSPF, it's actually the opposite of that. It means every interface has the protocol enabled. So if we look at the show OSPF interfaces, it would be now the inside, the DMZ, and the outside. So this is not really specific to the OSPF implementation on the ASA. It's just that in general, the ASA uses the subnet masks as opposed to the wildcards. But you can see which one it's taking when you look at the show run. If it inverted your addresses, then you know that you did it in the wrong format, that you used a wildcard and you should have used a regular mask. Okay, but this was what I was trying to do anyways, which was to enable OSPF on all of the links of the ASA. And now let's do that on the routers as well. So on router 2, let's say that on the link to the ASA, we're running OSPF area 0. And on our loopback, we're advertising our loopback into OSPF. Okay, and we can see that the adjacency forms. Basically what this is showing us is that on that outside interface, we do not need an exception that says permit OSPF to myself. So as soon as we turn the OSPF process on and it's listening on the outside, the ASA knows to allow OSPF to itself in this case. Okay, normally it's going to be dropped when the protocol is not on, but by enabling the process, it knows to listen for 224.0.0.5 and 224.0.0.6. Now, if we look at the routing table, we should see the loopbacks of routers 1 and 2 on the DMZ and the outside interfaces, respectively. Okay, so router 2 is on the outside, 1 is on the DMZ. If we look at router 1 and show IP route OSPF, we should know the route to router 2 because we're all part of the same OSPF process. Same is true in the other direction. On router 2, if we show IP route OSPF, we know the route to router 1. Now, this doesn't necessarily mean, though, that I'm going to be able to reach router 1 because the actual data plane traffic flow is going to be subject to the inspection engine and then any of the ACL exceptions that I have configured on the ASA. So on router 2, if I were to ping 150.1.1.1, I'm not actually going to be able to get there because the ASA is denying traffic coming in on the outside going to the DMZ. Because it says it came in on 0 and it's trying to go to 50. Well, that is not allowed because we're going from lower to higher. If it was the other way around, if we went to router 1 and said, can I ping router 2, this is allowed because of two things. We're saying we're now going from 50 to 0. Okay, that is allowed. We're trying to return from 0 to 50. It's going to say, okay, wasn't in the session table. So did you do an inspection for that protocol? In this case, yes, we did. We modified previously the global inspection policy on the ASA when we show run policy map to say inspect ICMP. So as the return flow comes back in, the ASA says, yes, this is true, so I'm going to allow the echo reply to come back. Okay, same would be true if we went to router 1 and tried to telnet to router 2. Because we're coming from higher to lower and then returning, the ASA is going to say on the return path, look at the connections, show connections. I'm expecting a return flow to come in on the outside, coming from router 2's loopback at source port 23, going back to router 1 on the DMZ. Okay, so I do not need an access list exception for this. Now, if we did want to allow unsolicited traffic from the outside in, like let's say we want router 2 to be able to ping 1, then we would need the ACL exception, because lower to higher security level is not allowed. So we would say here on the ASA, access list outside in, okay, that's the name of it. We're going to permit ICMP any echo. Okay, so we're going to allow pings to come in the outside interface. Then we apply it. We'll say access group outside in interface with the name of outside. Okay, now on router 2, we're able to ping 1. But what now about the control plane traffic going to the ASA itself? So router 2 for OSPF is generating packets going to 224.0.0.5 and 224.0.0.6 because this is a broadcast network type. So let's see, did that affect the adjacency between them? On the ASA, if we look at the show OSPF neighbors, and if we look at the dead timer for router 2, we could see it was 36, 33, 31, and then it refreshed to 37. So the new hello was allowed inbound. So the point being here is that this is an exception for the ASA. Control plane traffic to itself is not subject to the outside in ACL. So even though we have an implicit deny here, it's still being permitted because from an order of operations point of view, it's going to the routing process itself. Okay, we would see that if we look at the packet tracer and if we follow the individual flow, we could say it came in the outside and it was a raw IP packet that came from 136.1.215.2. The IP protocol number is 89 for OSPF. The destination is 224.0.0.5, so it's an OSPF hello. And it says that found flow with ID 378. So basically it means that it knows that internally the control plane is running this protocol. It does say that it's dropped because of an early security check. This is kind of an exception when you're doing the packet tracer to itself. But we could see simply based on the fact that the OSPF adjacency does not go down, that the ASA is allowing the control plane protocols to itself. So this is the type of behavior that you'll have trouble finding in the documentation explaining, is this explicitly allowed or denied? The easiest way to find these things out is just to try it out in the CLI. So if the control plane broke, we would know that there's a problem with the filtering and the order of operations. Now let's say we were to explicitly deny it. if we show run access list on the ASA, let's say we say for access list outside in to deny OSPF any. And before we do this, let's turn logging on. Let's say logging to the console at level 7, and logging is on. So we apply this ACL, show access list is going to show us the hit counter. And let's do this. On router 2, let's say clear IP OSPF process. Okay, that's going to reset the adjacency. So the neighbor is down. Let's see if they come back up. It says the process is full. So it's kind of a weird exception where iOS does not behave the same as this. On the router, if you were to configure an outside-in ACL to say drop OSPF, that would be processed before the routing process, the OSPF process, were to take over. But in the case of ASA, the order of operations is different. It's saying my local control plane is separate from the data plane filter you're trying to apply on the link. So if you want to, let's say, deny SSH traffic to the ASA itself, you wouldn't do that with an access list. You would do that with the command specifically that would be for SSH. Like to say that the host 1234 with the mask of all 255s is allowed on the inside. Okay, which then implicitly denies all other hosts from being able to SSH to it. But point being is that these separate local control and management plane protocols are outside the scope of the normal access list filtering. It's separate in the order of operations. Okay, the other feature that the ASA supports that is similar to iOS is reliable static routing. Now, like in regular iOS, if you've seen this implementation before, it uses two things, which is called the IP Service Level Agreement, or which was previously called the Response Time Report, or the RTR. This is going to be used to do our application level check, which in this case, the application level check is going to be a ping. Now, we don't have any very advanced SLA metrics like we do in iOS. Like in iOS, you could do a check based on doing an HTTP GET to your Apache server. Or you could do a DNS query to your bind server and figure out, is bind actually running and DNS is working. So in ASA, it's very simple. You're basically just going to ping the destination. If you get a response, this is then going to be tied to an enhanced object. And if the ping is successful, we say that the object is up. If the ping is not successful, the ping fails, the object is considered down. Now, the whole point of using this feature is that you then reference the object from a static route, and the route can only be installed if the object is up. So what this allows you to do is do reliable floating static routes, or to do reliable ECMP if you have multiple default gateways that are reachable on the same LAN segment. So as I mentioned before, the design that is not supported for ECMP is this one, where we have two different interfaces. Let's say that this is gig 00 and this one is gig 01. ASA is not going to be able to load balance between the two of these. Okay, it will be able to load share if the network looks like this, where we have the interface that is just outside, and then there are two equal next hops on that link. Now, the problem is, if we're doing static routing in order to reach these, how is the ASA going to know if router 1 crashes? Because if this is going to an Ethernet switch in the middle, we have a disconnect between the layer 2 and layer 1 status of the link versus the actual application reachability. So in other words, if router 1 goes down, the ASA is not going to know, because ASA is going to get the keep alive from the switch on the segment. This is the reason why you would want to use this feature, the reliable static routes. That you would say, ping the other end, ping router 1, and as long as I get my response back in, I'm going to install the static route towards them in the routing table. But if for some reason they go away, then I'm going to remove that. So let's say like in our particular case here, we have the outside interface that's going to router 2. So on the ASA, first let's configure our SLA instance. Okay, and again, under the documentation, this would be listed under the configuring IP routing. I want to say it's under configuring static and default routes. Here it is, monitoring a static or default route. This is the SLA monitor. Okay, so on ASA, let's turn logging off again, no logging console. We have an SLA monitor, we'll say entry number 1. And what is this going to do? The type is going to be to do a ping, an echo. Okay, so normally if you look at this in a regular iOS, there's tons of different options here under the SLA instance. But in ASA, it's basically just regular ping and that's it. Okay, so we're going to do an ICMP echo, and we're pinging to 136.1.215.2. The interface is my outside interface. And then we could specify some of the other sub options, like how often do I ping them? Let's say we ping them every 3 seconds. And how long do we wait before we declare them down? Okay, let's say that the timeout for the SLA monitor is 1 second. Okay, so 1,000 milliseconds. Okay, also here is kind of a side note. If you notice what happened when I looked at the question mark in ASA, this works different than it does in a regular iOS. Where in a regular iOS, when you look for context-sensitive help, it only shows you within the context of that individual parser sub-mode. So we can see here we're in a global config, we're under the SLA monitor, and we're under the echo config. So it says under SLA monitor echo, these are the commands. Okay, so that's the option. But also, there's hits for this under global config. So timeouts that relate to global connections or timeout options that relate to ICMP. Now you have to be careful of this in ASA because sometimes if the commands overlap, you may have meant to enter the command in one mode, but you accidentally entered it in global configuration because the syntax argument was wrong. Now the way that you can tell this is what mode does it return to once you enter the command. So here if we look at the option for that timeout, okay, timeout I'm going to have to give some other argument to. So let's say like timeout ICMP 0010. Notice when I enter this, it exits me out of the SLA monitor mode and it goes back to global config. This means that this was a global command, it was not under this particular mode. So we'll see that especially when we get to VPN, it's easy to make that mistake where you put something under global and not under like your group policy or your tunnel group, and it won't actually apply the way that we had meant it to. Okay, so let's say show run SLA. Show run pipe begin SLA. Okay, so we're pinging them every, actually I think the default is 5 seconds. Let's say show SLA monitor configuration for instance 1. Okay, we are pinging them every frequency every 60 seconds. So let's actually lower that. Okay, so SLA monitor 1, the timeout is 1,000 milliseconds, and the frequency, let's say, is every 3 seconds. Okay, now we need to start this. So let's say SLA monitor schedule, entry number 1, and let's say start this now, and the life is forever. Okay, so we're going to do this ping every 3 seconds, and it's going to continue as long as the ASA is running. Okay, otherwise you can do it time-based, of course. Okay, if we now look at the show SLA monitor operational state, I want to know what is the return code. And the return code, latest operation return code is OK. Okay, this means that we're getting the echo reply coming in from the neighbor. Okay, next step would be to take this SLA instance and then tie it to an object. So again, the SLA instance, this is just saying what's the metric that we're watching. The metric in this case is the ping. The object is going to call the instance, and then the object is referenced from the static route. Because from the static route, you cannot directly reference the SLA instance. Okay, so we're going to create an object. And actually it's called a track object. Track object number 1 is calling the SLA, or the response time reporter, instance number 1. That's the SLA number 1 that I configured. Okay, we want to check the reachability. So is the reachability okay or not? Now normally under regular iOS it gives you other options here like the timeout values and delays. In ASA it's pretty basic is what you can do with this. But the key of this then is to tie this to our static routing. So I'm going to say create a route on the outside interface that goes to whatever, 1234/32. And the next hop is 136.1.125, actually not 125, it is 215.2. But I only want to install this if track object number 1 is currently up. So if we look at the show track, it says right now the return code is okay. So reachability is up. If we show route on the outside, we see that the static route is installed. If we were to go to router 2, and let's do this, let's say on the link here that we change our IP address. Okay, we change our address to 215.200. Now, of course, OSPF can react to this because OSPF is dynamic, but if we were doing static routing, the ASA would not know that this route 1234 is no longer valid. So if we look at the track instance, the track instance says, well, now the ICMP echo from SLA instance 1 is down, or timeout more specifically. So it means that the track object is down. And then in the routing table, we can no longer install the route to that particular destination. So again, this is useful when you're not doing dynamic routing on the ASA. Normally it's when it's your edge device and you want to track reachability to one ISP, maybe of multiple outside interfaces. This would also be how you do routing failover when you are doing just static routing. So if we had that previous case where the ASA has separate outside interfaces. Again, the issue with this is that we cannot do ECMP in the ASA if you have separate physical links. So we could say that there's two static routes. There's one that goes 0000/0 via router 1, and one that goes 0000/0 via router 2, but we cannot use both of these at the same time. We cannot do active-active forwarding. We could, however, do active standby, say that this is the primary path and that this is the secondary path by configuring the track object on this route to ping router 1's address, and then on this route here, configure a higher administrative distance, which would give us basically the reliable floating static routes. So if we look at that in our case here, if we were to say And let's configure router 2's address correct again. Actually, before I do this, let's go to the ASA and add a new route. Let's say to get on the outside to 1234, we're going to use the next hop 136.1.215 dot anything, 123, but the administrative distance is 2. If we look at the routing table for the outside, it says to get to 1234, use this next hop. The administrative distance is 2. If router 2 configures its address correctly, which now is going to cause the SLA instance to heal itself. So if we show track, okay, now the return code is okay and reachability is up. And when we look in the routing table, we should now see that the static route is installed via router 2 with a distance of 1, as opposed to the previous one that was a distance of 2. So in other words, this is the backup route, and this is the primary route, the one with the lower administrative distance. So it essentially works the same way the logic does in iOS. It's just beyond this, there's not much routing features and functionalities that there is inside of the ASA. And we could see this from a documentation point of view. When we look under the configuration guides, let's say we look at configuring OSPF, RIP, EHRP, and multicast routing. Okay, if we look at OSPF, look at the features you can do. Okay, you could turn on OSPF, of course. We could do redistribution, we could do default routing, you could do summarization for either redistributed routes or inter-area routes. You could do some area filtering, like configure a stub area or an NSSA, and that's pretty much it. Okay, this one, defining static OSPF neighbors. This is if you want to advertise OSPF routes over a point-to-point non-broadcast network across an existing VPN connection without having to encapsulate the advertisements in GRE. Okay, that's the reason that you would do this with OSPF on the ASA, is that it doesn't support GRE tunnels. But for RIP, again, very straightforward. Okay, configure RIP, what's the version? What are the interfaces that it's running on? You could do summarization, you could do filtering, redistribution, and authentication. That's pretty much it. Same is true with EHRP. Okay, a little bit more advanced, you could do EHRP stub routing. You could do filtering and redistribution, authentication. But still, as compared to the regular iOS implementation, there's not as many features and functionality. Okay, also notice what other protocols are missing here. Doesn't support BGP, does not support IS to IS. Okay, IS to IS probably doesn't matter, but BGP could be a potential issue. Okay, we'll look at later when we look at TCP normalization on the ASA and how the inspection engine works. What are some of the potential problems if you wanted to route BGP over the ASA? So let's say you have a router on the inside and the outside. They're peering BGP, and then the ASA is in the middle doing inspection. There are some potential issues with the normalization engine of the modular policy framework, that the ASA is not going to automatically allow all of these type of routing sessions. Okay, when we look at multicast, multicast is even more straightforward. Basically, you enable PIM, you configure a rendezvous point, and then that's it. So it does not support dense mode, it only supports sparse mode. And if we look at the config, you basically just say multicast routing, and that's it. But again, we will come back to this. There's going to be a separate section that we're going to talk about multicast. So once we go through the transparent firewall, then we'll look at the difference in the behavior between the two of them. So multicast over the routed mode and the multicast over the transparent mode.